So hopefully you had a few minutes, maybe like 15, to work on this assignment, 15A. And then I did some of them with you and then we skipped some. So hopefully you had some time to work on those that you struggled productively. And let's do a couple more. Okay, so starting with number 2, find the volume, okay, in liters, obviously, of 0.300 grams of SnO2. Okay, and the density of this is blah, 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 blah. Okay, now this one is not actually a gas law conversion, because as you can see here, this S is for solid. So if that was throwing you off a little, I understand. But the point I wanted to make with this one is that we have to find the density. And I want to show you that finding the density of a solid, which you're used to, is no different than finding, like down here, the density of a gas. So I understand if that one was a little bit confusing. This actually is not a gas, it's a solid, but same logic for calculating density. Density equals the mass over the volume. Right now we have the mass. We don't know the volume. We're trying to find it, but we're given the density. So starting out with the number it gave us, 0.300 grams of SnO2. Grams on top means something with grams on bottom. I'm thinking this is our conversion, that there's 6.85 grams in a cubic centimeter of this substance. What is it? Sn is tin oxide. And a centimeter cubed is the same thing as a milliliter. Anytime you see centimeters cubed, you can replace it with milliliters. 1,000 milliliters are in a liter. And once you work that through, grams, cubic centimeters, milliliters, cancel. You'll have your answer in liters. And I hate this calculator. I don't know why my husband likes it so much, but he loves it and I hate it. So I'm not even going to use it to calculate a final answer. You'll need to do that on your own. But this is how you do the density. Okay, more on the density later. Number 5, what volume will 2 moles of nitrogen occupy at 720 torr and 20 degrees Celsius? Okay, so PV equals nRT. I've got, let's see, 720 torr. If I take 720 divided by 760, because there's 760 torr in an atmosphere. Okay, let me write this out. PV equals nRT. The pressure is going to be like that 720 divided by 760. That's how I'll get it into atmospheres. I don't know the volume. It's asking me what volume. 2 moles. So N with 2. R is always 0.08206. And the temperature to convert from 20 degrees Celsius to Kelvin, I'm going to add 273. Solving for B, we would multiply those and divide over the P. Make sure you get a final answer. Volume equals blah, 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 blah liters. What pressure will be exerted by 25 grams of CO2 at a temperature of 25 and a volume of 500 milliliters? So really quick, I need to take 25 and add 273 to get my temperature. And that's going to be, what is that? 25 plus 273. I probably should be able to do that in my brain. 298 Kelvin, and 500 milliliters converted to liters would be 0.500 liters. So I've got everything converted except for I need to get grams into moles. 25 grams of CO2. How many grams does 1 mole of CO2 weigh using the periodic table? Carbon weighs 12, oxygen is 16 each. So you, again, I'm not using this calculator, I hate it too much. You figure out the number of moles of CO2 that you have. Once you have that, PV equals nRT. You've got volume, you've got temperature, you'll have number of moles. R is always 0.08206. And you can solve for the pressure. At what temperature will 5 grams of chlorine gas exert a pressure of 900 torr and a volume of 750 milliliters? PV equals nRT. I'm solving for the temperature. I'm going to use this to find the number of moles. 5 grams of Cl2. Each chlorine, each Cl2 weighs however much. Use your periodic table. Whoops, I should have put grams here. Grams per mole. Then you'll know the number of moles. 900 torr. And there's 760 torr in an atmosphere. So that'll tell you your pressure. 750 milliliters is 0.750 liters. PV equals nRT. Solve for temperature. These next ones get a little bit tricky. We're trying to find the density and the molar mass. So, thinking about this for a second, density, just like we did up above, density equals mass over volume. Okay, so I somehow need to use this information to be able to solve for this. So first off, before I do anything else, let's do a conversion because torr and Celsius aren't going to work for this problem. 800 torr divided by 760 torr in an atmosphere. I guess I'll use this calculator. I just hate it so much. I don't like it at all. Okay. 800 torr divided by 760 equals 1.05 atmospheres. Okay, so this is equal to, and write it up here so I have a little bit more space. 1.05 atmospheres and 25 degrees Celsius is 298 Kelvin. So I got that converted. The equation that I normally use would be PV equals nRT. I'm trying to find density. I need mass over volume. I've got volume, and I can probably get the mass if I use the molar mass of this combined with the number of moles. So what I need to do is rearrange this equation, isolating the volume and the number of moles. I need to get them both on the same side. So let's divide over the V this way. We'll divide both sides by V. And let's see, so now N and V are there. Then we'll divide both sides by R and T. R and T over here. So this whole thing got rearranged into P over RT equals N over V. The pressure is 1.05 atmospheres. R is always 0.08206. The temperature was 298, and this equals N over V, which is not quite what I want yet, but I'm going to solve for N over V. 1.05 divided by 0.08206 times 298 in the denominator equals. Okay, I'm going to do some color coding, so maybe it makes it a little bit easier. All of that I just plugged in the calculator equals N over V. This number, 0.0429, equals N over V, so my units will be moles per, units for volume are liters. That's almost density. Density is mass over volume. And right now I have moles over volume. So the last step is just to convert and say, okay, let me get a scratch paper so I don't run out of room. My scratch paper would be 0.0429 moles of this substance. How many grams is that? So 0.0429 mole NH3. 1 mole of NH3 weighs, I think it weighs 17, because this weighs 14. And there's 3 hydrogens that each weigh 1. So that weighs 17 grams. So I've got 0. I'm going to round this number, 0.73 grams. Cool. So let's plug this in. My density would be 0.73 grams. That's the mass. divided by the volume. We already have the volume, grams per liter. That is my final answer. Mass over volume. I used Pervnert to get moles per volume and used the molar mass to get it to grams. Another density one. If the density of the gas is 1.2 grams per liter at 745 torr and 20 degrees Celsius, what is the molar mass? In this case, we're trying to find molar mass. The units for molar mass are grams per mole. This is what we're aiming for. We know that the density is 1.2 grams per liter. Okay, we'll use that in a moment. 745 torr. Not digging that one very much, so we can, let's divide that to figure out 745 torr divided by 760.98 atmospheres. 20 degrees Celsius converts to 293 kelvins. Okay. So similarly to like we did up here, we need to rearrange our PV equals nRT and do like a slight variation. These problems are kind of tricky. We already arranged it over here, so I'm actually going to keep it being the same because we already, like I already showed how to do this. PV equals nRT, I can arrange to P over RT equals N over V. It's important that I have N over V on this side because N over V, I can do a small modification to be able to use grams per liter instead of number of moles per liter. So when I plug this in, pressure, the pressure was 0.98 atmospheres divided by R is the universal gas constant, temperature 293 equals N over V. Okay, so here's my work again. Sorry, I had to pause the video. My dog was barking. So I plugged in pressure, R, temperature. I'm solving for this ratio of moles over volume. And when I punch in this into the calculator, I'm getting that that equals 0.0407. The units would be moles per, it's getting squishy, moles per liter. Now I can use this to kind of help cancel some things out. 0.0407 moles per liter times, copy paste this chunklet here. Let's see, let's flip it and put liters on top. 1.2 grams per liter. I can plug in ones if I want. Liters will cancel with liters. When I get this answer, my units will be moles per gram. That's not quite what I want. I want grams per mole, but that's super easy to fix here later on. So let's see. 0.0407 divided by 1.2 equals 0.0339 moles per gram. So in order to get this flipped to be grams per mole, I'm just going to take 1 divided by this. And that will equal grams per mole, which is what we were aiming for. So 1 divided by that equals, I'm getting that my molar mass would be 29.4. That's how many grams are in a mole of that. This is how much it would be if whatever this gas was, you looked it up on the periodic table. That's your grams per mole. So those ones with the density are really tricky. It basically boils down to you need to rearrange into this formula from PV equals nRT. And you have to use this ratio N over V really sneakily in order to calculate grams or liters. Okay, last one's number 10. How many moles of nitrogen gas? Now remember, nitrogen gas is one of those atomic ones that's in pairs, N2, because we're going to have no fear of ice cold beer. Those are our diatomics. Nitrogen is in there. Not sure if that's relevant for this problem, but I wanted to label it anyway. How many moles of nitrogen gas will occupy a volume of 347 milliliters is 0.347 liters at, okay, 6,680 torr. That's a lot of torr. 6680 divided by 760. Apparently we're working at 8.79 atmospheres today. 8 times the pressure of the Earth. Maybe we're on a different planet. And 27 degrees Celsius turns into 300 Kelvin. PV equals nRT. Do I have all of it? I have P. I have V. I always know R, 0.08206 in this context. I have temperature. So it's not actually relevant that it was N2, but when I solve for N, I would get my number of moles. What volume will 1 pound of hydrogen occupy? Again, hydrogen would be a diatomic. I'm not sure if that's particularly relevant in this problem or not, but it would be H2. I have 1 pound of it, 454 grams. I need to do it is relevant because I need to do a grams to moles conversion. 454 grams of H2. How many grams are in a mole of H2? Because I need number of moles. Let's see, PV equals nRT. I just got number of moles. I always know R. The temperature is 25 degrees Celsius, so that's going to convert to 298 Kelvin when I add 273. I've got nRT. I'm solving for the volume because I already have the pressure. 1.05 atmospheres. So 1.05 solve for V equals whatever that number is times 0.08206 and a temperature of 298 Kelvin. On the back side, there are two questions regarding density. You have the density of helium gas and the density of an unknown gas. We don't know what it is, and you're going to find, oh, sorry, if the density is this, then what is the molar mass? You're actually finding the molar mass on that one. For these problems, they're very similar to the ones on the front. I am going to only give you the final answers and let you see if you can figure out how to get there. So for number 12, your final answer is going to be, you're trying to find density. Density equals mass over volume. So your units should be something like grams per liter. And your answer, when you're done, will be 0.0545 grams per liter. So show how to get there. The next one, you're trying to find the molar mass. The molar mass is grams per mole. And the final answer for this one is also 29.4. Actually, is this the same problem as the one on the front? Because if so, you just get a freebie point. Let's look. Yeah, it is. You don't have to do this one. It's the same as on the front. I must have forgotten to erase it. So really, you're only doing this one for the helium gas. Now 14, 15, and 16, here's a really cool trick for doing these. It's changing one of the variables and asking you to predict how the gas will respond. So for number 14, it says we have an ideal gas. It's occupying a volume of 10 liters at 27 degrees Celsius. Okay, that's our initial conditions. The pressure is tripled, and consequently the volume is going to change. To what value must the temperature change to restore the volume of the initial 10 liters at the new pressure? You see how this works? They're kind of weird. Like this next one, if a gas occupies a volume of 1 liter at 30 degrees, the temperature increases by 10. What does that make our volume need to expand to in order to keep the pressure constant? So back in the notes, you could, see, oh, is this Boyle's law? Is this Charles' law? Is this Avogadro's law? And think about these separately, like what is the relationship between volume and temperature? What is the relationship between pressure and volume? But here's my trick. I don't even know those laws. I'm not joking with you. I do not know that Charles' law is V1 over T1 equals V2 over T2. I don't know that. What I do know is the ideal gas law, and I know how to rearrange stuff based on algebra. So for number 15, let me just write it this way. You know that PV equals nRT, right? Now, watch up here. Could I say PV equals nRT? Could I do this? Could I do nRT equals PV? Are you okay with that? Are you okay with instead of PV equals nRT, nRT equals PV? Because if you're okay with that, then what I'm going to do is uncover both sides so that we have PV equals nRT equals PV, and I'm going to get rid of the middle part. PV equals PV. Cool. Yeah, without even knowing, I came up with Boyle's law. When I need to know the relationship between P and V, I wrote it out and canceled the rest. So let's see, I don't know exactly which one I need for number 15, but let's see which one I need. An ideal gas occupies a volume of 1 liter at 30 degrees Celsius. If the temperature increases, what would, okay, so it's talking about volume and temperature. Those are the values I have. I have the volume, I have the temperature. So when I do my little rearrangement here, normally we would just write this as PV equals nRT. I first need to get volume and temperature on the same side of the equation. So let's rearrange this. I'm going to divide over the T and divide over the P this way. So by the end of it, I'll have V over T equals NR over P. That makes sense? Rearranged. If you're okay with that, V over T equals NR over P. Can NR over P, can I say that equals VT? Can I rewrite it? Yeah, this way, both ways. Get rid of the middle. V over T equals V over T. Double check the coolness. Whoa. V over T equals V over T. That's funsies. So let me write the equation out on my paper. V over T equals V over T. Technically there's, V1, T1, V2, T2, and that's fine, but it's implied, right? Like I have two sets of conditions, so I need to keep them straight. The first set of conditions tells me that I have 1 liter and a temperature of 30 degrees Celsius, which is going to be let's see, I did not do that right. 30 plus 273, 303. Okay, so on the one side we have V and T figured out, and now we're wondering on the other side, it says the temperature increases by 10 degrees Celsius. Celsius and Kelvin are pretty much the same, just shifted. So 303 is going to increase to 313 Kelvin. So we've got almost everything figured out, but we still, we need to solve for what the volume would need to expand to in order for this to work. So plugging this in my calculator, I'm going to cross multiply and divide to solve for this, because basically I've got 1 over 303 times V over 313. So cross multiply and divide. 1 times 313 divided by 303 equals, sorry, let me scoot that up. 1 times 313 cross multiply, divide 303. My volume would need to expand to 1.03 liters instead of just 1 in order to keep the pressure constant. The next problem deals with a fixed amount of gas at 25 degrees Celsius. Okay, so we have temperature and it occupies this much volume and the pressure is this many torr. Now, even though it told us that the pressure was 629 torr, it actually doesn't matter because we want to maintain the pressure at 629 torr. So I'm actually going to cross this out. It's kind of irrelevant that they told us that. That was just to like lead us off the trail. But really it's between the temperature and the volume. And again, the temperature is changing. So I'm just going to reuse my same formula that I had above, where it was V over T equals V over T. You can learn how to derive this like I showed you using the gas laws, or you can actually take the time to learn these equations. V over T equals V over T. On the one side, we've got 25 degrees Celsius, which I think is 298 Kelvin when you convert it. The volume, it says, is 10 liters. I'm trying to, again, calculate the volume, but after my system has adjusted, so I'm going to be solving for the V on this side when the temperature is increased to 121 degrees Celsius. I don't know what that is in kelvins. 394. Cross multiply and divide, and you should be able to get your new volume in liters. And last problem that we skipped, number 14. An ideal gas occupies a volume of 10 liters at 27 degrees. Okay, the pressure is tripled. Oof. The volume changes. What value must the temperature change to in order to keep the volume the same? So yes, the volume is 10, but nobody cares because we're trying to keep the volume at 10. So realistically, the only variables that are changing are temperature, and the pressure on the gas is tripled. Okay, so what's the relationship between pressure and temperature? PV equals nRT. I need to get P and T on the same side. I'm going to divide both sides by T. I'm going to divide both sides by V. And I'll end up with P over T equals NR over V. If P over T equals NR over V, then NR over V equals P over T. Yeet. P over T equals P over T. I like this version better than any other version because this is an example where like there actually isn't necessarily a law that combines P and T. There's P and V, there's V and T. You'd have to put these together, substituting the V in order to do what we just did pretty simply. So I love this method. It's so easy. So let's see. Copy paste. We got P over T equals P over T. That's my formula. And in the first circumstance, it says the temperature is 27 degrees. That converts to, let's see, 27 plus 273, 300 Kelvin. So in the first condition, I have 300 kelvins for the temperature. And I don't know what the pressure is, but I'm going to say that the pressure is equal to 1. So that way over here, when it says the pressure is tripled, I can just put a 3 here. 1, 3. I guess if you wanted, you could do 3 and 9, but since it didn't give us a value, I can just plug in the ratio. It went from 1 pressure to 3 times that pressure. And we are trying to find the new temperature, cross multiply and divide. 300 times 3 divided by 1. The new temperature would be 900 kelvins.